Welcome to a lesson with Dr. Powell. Let's take another look at the example that we had of a simple Graham-Schmidt process. We had three vectors in R4 that create a three-dimensional subspace of R4, and we orthogonalized them to this. Now, in the other video, what we did is we used dot product and projections. Here we're going to do the exact same thing, but in the guise of matrices. All right, so how do we do it? Well, for starters, the first guy is going to be the first vector, right? So from here to here. So W1, W2, W3 are going to be our new vectors. W2 is going to be this vector, thought of as a column. So notice how we're thinking of all our vectors as columns now. Okay, so this vector, and then we're subtracting off this matrix multiplied to this column. Now, you see this down here? That's actually a scalar. So like we're dividing by a scalar, so we're multiplying by 1 over the scalar right here. This is really just the dot product between of this with itself, which is the same thing as W, the length of W1 squared, if you will. It's just the sum of squares of entries of W1. You could also write it out if you wanted to like this, -1, 0, 0, 0, -1, 0, 0, 0, and then you actually see that times that, plus that times that, plus that times that, plus that times that, and it would just give you 1 in the end. Okay, in this particular case. So that's nice. All right. So really it's just this. Now what is this? This is this matrix product. Now if we do a column interpretation, this means that in the first column over here, we just want -1 times, we just want -1 times the first and only column right here. It's just, so this is just this times that column. That goes there, and then that times the column goes to the next spot, and that times the column goes to the next spot, that times the column goes to the next spot. So really what we see clearly is just like the first column is just simply -1 times this column, which is just 1 with zeros, and the rest are zeros. So this matrix shouldn't be hard to see what it is. You take this matrix and you matrix multiply by the column V2 on the right. Now, doing so, let's think about that. -1, so to multiply that, simply what we're doing is -1 times the first column plus 0 times the second column plus -1 times the third column plus 0 times the last column. Really what we end up getting is just simply, because we have lots of zeros, just simply -1 times that first guy. So what we end up getting is, at least this part right here, ends up being simply -1, 0, 0, 0. And we're subtracting that. So in the subtraction becomes a plus when we're adding it on to the V2, which will make this first entry go away to be a 0. So we end up getting this as our W2 right there. Not too bad using matrices there. Now, there's pros and cons to both techniques. Either just thinking about it in terms of dot product or matrices, but honestly, they're the same in the end. The calculation is exactly the same, just looking at it in different ways. Here, there is kind of a nice visual benefit because we can just matrix multiply the V3 once, like the V to a matrix, because we can just keep on expanding this matrix right here. Well, not really expanding it, just adding onto it. So this matrix and this matrix are the same size. We do the same thing that we did to get this one by over here, but with the W2, what we just found. So this is an inductive or recursive type process. So if we take W2, which is this, and we multiply it with its transpose, you can see what's happening right here. We end up getting something just like this, really like negative. So the third column will just be -1 times that column, 0, 0, 1, 0. Everything else is zeros in the matrix. Okay, so we take that and notice that W2 transpose WT, so just the dot product of this with itself, or the length of it really, squared, is just 1. Okay, so when we take this matrix and divide by 1, it's still the same thing. So basically it's just this times V3. Well, not quite, right? It's this thing right here is this part, but we have to add it to B1. Okay, we have to add it to B1. And if we had even another step, this would be our B2, and then we just say B2 plus the next guy that we have, where it's always just one back in the recursion. Okay, so we just add B1, which is this one, to that one to get this, and that's what we matrix multiply to V3. Right? So we only have one matrix multiplication to a column. The rest is just addition, for this particular example, it's so nice because there's so many zeros that it goes very quickly. Now, right here, so we matrix multiply this to this column right here, column vector V3. And what does this mean? This means 1 times the first column plus 1 times the last column, which ends up just giving us 1, 0, 0, 0 itself. So that's what we subtract off from V3. So V3 minus that ends up giving us this, just as desired. So this is the outcome. What it is it's a basis of the exact same subspace that we started with, but this time it's orthogonal. Each thing is orthogonal to every other thing. So this is orthogonal to that. Imagine taking a dot product, you get 0. I mean, here it's 0 very clearly. And from here to here it's 0. All the way around, every pair gives us something that's 0. And so it works. Thanks for watching.